Okay, everybody, moving right along. We are now going to talk about higher derivatives. We've already talked about this a little bit, but we're formally just going to introduce them and introduce the notation. Okay, so let's say you differentiate a function and you want to differentiate again. In terms of vocabulary, we call this the second derivative. And in terms of notation, what we do is we write f double prime of x, or if you want to, d squared f dx squared. And the reason why we don't put the 2 after the f and after the x is that could get confused with df dx, whatever that is, squaring it. And we don't want to do that. So that's why they do this notation like this. For people who are taking physics, sometimes they'll also go like double dot here, f double dot of x. Now the third derivative, so if we differentiate again, third derivative of a function, in terms of notation, okay, usually we'll do f triple prime of x, or we could go d cubed f dx cubed, or even though it's not common, you still can do this triple dot. After the third derivative, the dot notation is not usually used. So in general, if you want to write the nth derivative, okay, if you don't like the triple prime, for example, you can also do it the way I'm about to show you. A general derivative, an nth derivative, we say f to the power of, we go bracket n bracket x, or dnf dxn. Once you start getting past the third derivative, this notation is more used, but sometimes you see this when you're doing a series and sequence for calculus. All right, now let's just do a couple of quick examples, okay? Let's say we have this polynomial. Let's find the first three derivatives. Okay, so my f prime, by power rule, I have 3x squared plus 12x minus 9. I differentiate again. I just look at this like the function, like the starting point. So I'm going to get 6x plus 12. Now say I wanted to then differentiate the second derivative. Again, just think about this as the starting point. So this is just going to be 6. And if I differentiate it again, so if I said, you know, f2, I could write it like that if I wanted to, or I could write it like this. That would just be equal to 0. All right, now let's say that our function's equal to y, so we'll do the dy dx notation. Okay, by chain rule, I'm going to bring down my 2, ignore the stuff on the inside. This is now to the power of 1, and the derivative of the inside is just 2x. Okay, so I'm going to bring the 2x up front with the 2 to give me a 4x, and then I have x squared minus 1. Now, if I want to differentiate this again, okay, I have to do the derivative of the first times the second plus the derivative of the second times the first. If you wanted to first expand this into a polynomial and then differentiate, that's also fine. I'm just going to do it with the product rule so we get some extra practice. So the derivative of the first is 4. The second is x squared minus 1 plus the derivative of the second, which is 2x, times the first, which is 4x. Okay, so if we expand this, what do we get? I'm going to get a 4x squared minus 4 plus 8x squared. So I'm going to get a 12x squared minus 4. If I differentiate it again for a third time, that's just going to be by power rule 24x. If I differentiate a fourth time, I get 24. And if I did a fifth time, then I'd get 0. So when you have polynomials, eventually you'll get to 0. But what about if you have trig functions, sines and cosines, where the derivatives are each other, basically? So let's first look at g prime. So the derivative of cosine, sorry, gave it away. The derivative of sine is cosine. So g prime is cos x squared times the derivative of the inside, because we don't just have an x here on its own. So 2x. And I'm just going to rewrite it so it's easier for me to look at 2x cos of x squared. To differentiate this now, I got to do product rule. Okay, so derivative of the first is 2 times the second plus the derivative of the second. Now I'm going to put brackets here because the derivative of cosine is negative sine. So I have negative sine, leave the inside, then by chain rule, take the derivative of the inside, that'll give me a 2x, and then multiply all that by the first. Don't forget about that first. So let's simplify this a tiny bit. So I have 2 cos x squared plus, no, minus. I'll multiply the 2x and 2x together, bring it up to the front, so that will give me a 4x squared sine of x squared. And now the third derivative is even more fun. We get to do, the first one's at least nice. This is just going to be 2, the derivative of cos is sine, negative sine, that Janelle, negative 2 sine x squared times the derivative of the inside, so times 2x. Now I'm going to put minus and do big brackets so I don't mess up signs here. So for the second term, I'm going to have to do the product rule. So the derivative of the first, which is 8x, times the sine, plus the derivative of the second, which is going to be cos x squared, times 2x, and then multiply that by the first, which is a 4x squared. Remember, I factored out that negative, so I don't have to worry about it. And now let's see what I have here. So now for my first term, I'm going to bring the 2x up and multiply it by the negative 2. So I have negative 4x sine x squared minus what? 8x sine x squared. Now minus distributes, so I'm going to minus. I'm going to bring the 2x and the 4x squared up front and multiply them together. So that will give me an 8x cubed. And then that's cos x squared. And I can simplify it a tiny bit more because I have x sine, minus 4 of them here, minus 8 of them there. So together I have minus 12 of the x sine x squared term. And then my cos term, I have minus 8 x cubed cos x squared. And the more you differentiate this, the prettier it'll look. Okay, good times. Now, since many of you are taking physics, we've talked about this a little bit anyway, but velocity and acceleration. Now, velocity acceleration, if you have a position function and you differentiate it, that's referred to as velocity. If you take the instantaneous rate of change of velocity, or basically differentiate velocity again, this is called acceleration. And most people will understand, velocity and acceleration in terms of a car. You can be going at a constant velocity, but you can also be accelerating. Okay, where velocity is the instantaneous rate of change of distance. So say that your s of t represents your distance. Then typically in terms of notation, we call velocity v of t, and we find it by going d dt of s of t, which is the same as saying s prime of t. So some people will use s prime, some people will say v of t. That represents velocity. And acceleration, similar thing. Okay, we sometimes call it a of t, and we find it by going d dt of the velocity, which is equivalent to saying s double prime of t. So now, in terms of what happens if these things are positive or negative. So say we have a car. Now let's take a look at what it physically means if the velocity and the acceleration are positive. Think if you were driving. Well, your car is going to be speeding up in the forward direction. So the car is speeding up. Okay, and I'll put here forward direction. Okay, just to make sure that's clear. Now, what happens if your velocity is positive, but your acceleration is negative? Okay, your acceleration is negative. It means that you're still moving forward, but your car is slowing down. Think about when you start pressing the brake. Now, what happens if your velocity is negative, but your acceleration is positive? So you're backing up and slowing down. Okay, so your velocity is negative, but your acceleration is positive. So the car...
Is there something else I can help with?
No, Siri? Nope.
Okay.
Siri apparently found that interesting. The car is backing up. Elon's like, I want the data. Give me the driving data. And slowing down. And then if both velocity and acceleration are negative, you're speeding up in reverse. All right. So hopefully that will build some intuition for you. Thank you very much.